SwayamPrabha. Digital India. Educated India.
Welcome back. So, in today's class we will continue discussing on carbon nitrogen bond formation reactions. We have seen in the last class that how ligand can influence each and every process, each and every step of the palladium catalyzed carbon nitrogen bond formation reactions. Of course, if a very easy combination is there, let us say a aryl iodide is there and a very good amine such as your aniline is there, then we can have corresponding diaryl amine synthesis pretty easily. So, it all depends on the type of substrate we are dealing with. If the combination is very easy, two combination you need for cross coupling reactions. If both the substrates are suitable for the coupling reaction, we will get a reaction pretty easily. However, if any of the component becomes difficult, then we really need to see what best we can do for increasing the yield and efficiency of these processes, and that is where the ligand design can be extremely crucial. If there is a easy combination, you can get the reaction even with triphenyl phosphine, but lot of cases or most often than not, what we have seen that the triphenyl phosphine or other easily available ligands which are we are more familiar with are not sufficient or efficient enough to carry out the coupling reaction. Remember, most important things for this type of coupling reaction is to reduce the palladium loading, reduce the time, reduce the temperature, and every possible things, every possible parameters one can optimize to get these reactions going in a greener way or in a better way. That is something all are looking for. Now, in order to get a lower catalyst loading or in order to get a better and more efficient reactions, we usually have to deal with a ligand. We should have a system, we should have a catalytic system that is going to be very, very efficient, and this is where ligand plays a crucial role. If the ligand metal complex is very efficient for a given process, then the overall palladium loading goes down, and that means that the removal of the palladium is not a big problem for pharmaceutical industry. Well, of course, the cost of palladium one has to look at once looking at any given reaction. Now, we have seen for the biaryl phosphine ligand how it can bind with the palladium center and what it can do in doing the oxidative addition, amine binding, deprotonation and the reductive elimination process. Let us look back at those drawings once again to appreciate the fact how good this biaryl phosphine ligand might will be for these palladium catalyzed carbon nitrogen bond formation processes. So, what we have right now is the same drawing what we have tried to do in the last class. Now, we have it in ChemDraw fashion already ready. What we do see that the palladium is coordinated with phosphine ligand and interacting with the bottom phenyl ring, and from this conformation this palladium is on top of the phenyl ring, it is not the other side. Palladium is not on the other side because it is having low coordination, it prefers to have this coordination from the bottom phenyl ring. Now, after this we will have the oxidative addition, we will have the oxidative addition into aryl chloride or chlorobenzene in this case to give rise to an intermediate where palladium is 1, 2, 3 and 4 coordinate. And subsequently what we can have is the amine coordination, but amine coordination in this geometry is not going to be possible. What then happens is palladium flip over on the other side while amine is coordinated with palladium. So, palladium is no longer towards the bottom phenyl ring. So, it is swipe or it is like swing away from the bottom phenyl ring. So, basically a C palladium bond CP bond rotation gives rise to the orientation where palladium is far from the bottom phenyl ring. Under that condition, we can have the deprotonation also pretty easily. Once deprotonation is happening or happen, then it can come back, because during the deprotonation we lose HCl overall, and then it becomes a 3 coordinate from where if we are to get a reductive elimination, we need to create an atmosphere which is sterically crowded. If it stays on the other way around after deprotonation, then it is less sterically crowded. By bringing back the palladium on top of the phenyl ring, it again regains the steric crowd, which will be essential for the reductive elimination step. So, this is essential for the high efficiency and turnover number for the palladium to come back on this side, and there is enough evidence in support of each of these steps at this point in the literature. Now, if you look at very carefully the step before the reductive elimination, the materials before the reductive elimination. Okay, let us look at it once again, what is important and what can give rise to a pre-catalyst like design from this transmetallation or deprotonation intermediate. Okay, let us look at it. So, if you look at this intermediate where you have palladium, ligand, NH and phenyl, right. This orientation over here is extremely important to note, where we have the palladium over there and phenyl over there, and phosphine ligand is coordinated with it. This is the aryl ring and this is the NH and this is the ligand. Now, keeping that in mind, what people have done is come up with a design for the pre-catalyst. Let us look at that pre-catalyst design. So, remember we have a palladium, aryl, amine and a phosphine ligand coordinated with palladium. Now, how can you design the pre-catalyst from such a orientation which will be essential for our pre-catalyst design? Okay. We do have a phenyl ring and we do have a palladium with it, right, and then there is a ligand with it. Now, before the deprotonation, what we were having is NH, R prime and R2 and chlorine, right. Now, looking at it, what scientist has designed, this is once again by Buchwald group at MIT, they have come up with a design which showed that if you can combine this aryl moiety with this amine. So, that means an intramolecular setup, okay, where NH2 is given. Now, palladium LCl. Now, this is the ligand, that biaryl phosphine ligand we are talking about. This is the same ligand we were talking about. What we have essentially done is the C palladium bond, we kept it constant. From the ortho position, we have attached the amine. Okay. Now, this is a material which one can synthesize and stabilize and keep it without any problem in solid state. So, therefore, this material can be procured from the chemical company. Now, in presence of base, what can be done simply is we can get rid of HCl from this intermediate, right, and therefore, what essentially we have is a palladium ligand and this deprotonation intermediate. From there on, we will get ligand palladium 0 after reductive elimination of the intermediate to give you the product like indolein, right. Now, in this reaction, what essentially we have seen is very simply by putting the oxidative addition and amine coordination into the picture, and now design in a way so that your two coupling partner are attached with each other. So, this is more of an intramolecular reaction. Of course, this reaction ideally we are not interested in, because this is an easy reaction, and taking advantage of this we can get an oxidative addition into that amino aryl chloride moiety, where ligand is attached with it. Now, if we have this material readily available from commercial source, at that point what we can have is the oxidative addition intermediate in presence of base and heating can gives rise to the deprotonation, subsequently reductive elimination to form the product, which is something we are not interested with. This can come up in, let us say, if we are using 1 mole percent of this catalyst, this can form in 1 mole percent, but what it gives you is a clean formation of ligand palladium 0 in 1 mole percent. During the process we do get the indoline as the product. Now, so what essentially in this case we are trying to come up with is a method that gives you a clean, let us say 1 mole percent of palladium ligand 0 complex formation. This will be essential for very low loading and low and very high turnover number and frequency of the catalytic cycle, because if the ligand palladium 0 complex can be synthesized pretty easily without any loss in efficiency, that will be essential for a highly efficient reaction. So, therefore, taking advantage of the known catalytic cycle, a pre-catalyst can be designed which can readily supply the ligand palladium 0 along with formation of the organic compound, which is, let us say, will be formed in equivalent quantity as we need the ligand palladium 0 species. For example, if we need 0.001 mole percent of palladium for a reaction, then 0.001 percent of organic molecule will be generated during the reaction, which is negligible amount. Now, 0.001 mole percent of this palladium with ligand can be generated very efficiently and very precisely in the reaction mixture. That gives us the opportunity to do the reaction in very high efficiency for a given carbon nitrogen bond formation, because the ligand palladium 0 that is getting generated during the process will be then participating in the real catalytic cycle. So, this is a method all to prepare the ligand palladium 0 in situ. All right. Let us move on then the discussion of some other processes where we will be seeing the role of metal, mainly early transition metal, for the cyclization processes. Okay. Now, we will bring a new topic at this point to discuss the cyclization processes or oxidative cyclization processes, where once again metal plays a critical role to bring two or more unsaturated moiety together, so that new carbon-carbon bond formation is happening. Okay. Essentially, in this next process, oxidative cyclization process, we would like to look at how, let us say, for example, alkyne and olefin are put together to give rise to value added product. These starting materials are readily available, but one need some metal complexes to come up with the cyclization process or a desired transformation process, which can give the added value to these commodity chemicals. Let us look at the oxidative cyclization and discuss more on that right now. So, we are going to discuss oxidative cyclization in the process of doing these transformations. Oxidative cyclization. Okay. Now, this is a process where a ligand metal will interact with alkyne and another alkyne or another olefin. Overall, if ligand oxidation state is Y, for example, and we will get in the product ligand metal oxidation state change to M+2. If it is Y, it should be Y+2, and along with it we can have the olefin binding with it. So, overall alkyne and metal interacts to form a cyclopropene type metallocyclopropene intermediate. Therefore, metal oxidation state goes up from Y to Y+2. Subsequently, we can have the insertion method, insertion process into this metallocyclopropene ring to incorporate or to form a 5-membered metallocycle intermediate. So, these two carbon centers are coming from this olefin and these two are from the alkyne. If it was two alkynes, alkyne and alkyne, and then we should have another double bond over there. Usually, we have early transition metal for these processes. Early transition metals are usually used. Of course, another important thing we can discuss in this banner is the Poisson-Cohn reaction. That is a very powerful technique, and lot of natural product are synthesized by utilizing this technique. Not only two partners, we can also have even the 3 coupling partners. So, we can have cyclotrimerization by utilizing this technique. Well, essentially this method gives rise to a situation where early transition metals are used to couple 2 or more unsaturated unit together to form the new carbon-carbon bonds. Essentially often gives rise to the cyclic compound formation, which otherwise from these commodity chemical, from these easily available chemical would not have been possible. We have seen right now an alkyne can be reacted with an olefin, to give you the cyclopentene intermediate, metallocycle intermediate. We can also have 2 different alkyne to gives rise to the cyclopentadiene type of intermediate and the metallocyclopentadiene type of intermediate. Essentially, we would deal with the early transition metal. We are also going to discuss the Poisson-Cohn reaction, which is the extension of this type of reaction. Additionally, of course, one can think of 2+2+2 cyclotrimerization reaction by utilizing this technique to give the value added product formation. Let us look at the early transition metal processes, or what are the different category of these processes that will be involved in this oxidative cyclization technique. So, we are going to look at oxidative cyclization processes where these early transition metals are involved. Early transition metal mediated oxidative cyclization processes. Well, first we will deal with the reactive metal fragment. Okay. In this process, we will see that an alkyne is reacting with, for example, another alkyne to give you the metallocyclopentene intermediate. So, we have a ligand metal reacting with an alkyne to give rise to the ligand metal alkyne interaction at the beginning. Subsequently, this intermediate, so if it is metal N plus, it would be N plus at this stage. Subsequently, ligand metal can gives rise to the N+2 if it is N plus intermediate, to gives rise to this metallocyclopropene intermediate. From there on, another alkyne, for example, can interact with this ligand metal cyclopropene intermediate to form the cyclopropene alkyne interaction. Subsequently, insertion of this alkyne into this cyclopropene intermediate will give rise to the 5-membered intermediate that can be further utilized for value added product synthesis. So, this is by Nigisi, and you can read the comprehensive organic synthesis book for this purpose, okay, chapter 9.5. Now, in this case, what exactly we have seen is two different alkyne. One alkyne is interacting first with the metal center, forming the cyclopropene ring, metallocyclopropene ring, and subsequently this metallocyclopropene ring interact with another alkyne to incorporate that as well. In the process, we see a new carbon-carbon bond formation and two different metal-carbon bond formation, therefore, two new metal-carbon intermediate and one new carbon-carbon bond formation process is happening. In the process also, we see that if the early transition metal is starting with N plus oxidation state, it ends up with N plus 2 oxidation state in the process, and once having this cyclopentadiene type of intermediate, this metallocyclopentadiene intermediate can be further reacted, because two metal carbon reactive intermediates or reactive bonds are there. Those can be, for example, protonated, or other insertion reaction can be possible at those stages. So, let us look at other type of this oxidative cyclization method that will be involved during the reactions. Okay. Another important thing that can happen is the beta abstraction. Well, that is a very novel technique reported by Buchwald in 1993 in Science paper, where ligand metal is reacted with olefin to form a ligand metal alkynyl and alkyl intermediate together. From here on, there is no option but to undergo a beta abstraction, right. So, metal oxidation state is such that it will not be undergoing a beta hydride elimination, only option it has is to undergo beta abstraction. So, this is a beta abstraction process. Overall, we get RH out of this process, okay. But once again, this is not a beta hydride elimination, this is beta abstraction. The electron required for metal center is not available for the beta hydride elimination. Therefore, only option that is available is beta abstraction, and then ligand metal, this alkyne intermediate is formed from this, which can be essentially nothing but that what we have seen previously. It can undergo the cyclopropene ring formation. From there on, a you can have an alkyne, it can be internal, terminal, any different alkyne can be possible, and ligand metal alkyne then interact with the cyclopropene intermediate to gives rise to a intermediate where we can once again get the cyclopentadiene species, which can then be further reacted to give us the desired product that we would be looking for. So, this is the method which is a beta abstraction method, and that is very powerful in delivering the desired compound starting from this ligand metal alkyl and alkynyl intermediate. In this case, what we have seen that a beta abstraction is the only process, and thereby the starting process with the beta abstraction gives rise to the metallocyclopropene intermediate, where oxidation of the metal state happens to by +2, and then another olefin or another alkyne can react to give the metallocyclopentadiene intermediate, for example, what we have discussed today. Yet another type of this oxidative cyclization is possible. Let us look at that. This is almost a mixture of method which can be classified under the oxidative cyclization process. So, hybrid method for dealing with this oxidative cyclization process. We are now looking at a method which is a combination of these processes, ligand metal and cyclopropane ring is there. From there on, the alkyne will be reacted with it. During the process, this olefin fragment will go out, and overall we have ligand metal alkyne species formation, which is nothing but once again this ligand metal cyclopropene formation. From there on, the alkyne can react. First it has to interact with the intermediate, and subsequently we will see the incorporation of this alkyne into this metallocyclopropene intermediate to form once again the similar processes. Okay. So, from here on we will discuss various type of reactivity by utilizing this oxidative cyclization technique, that we will be discussing in the next class, mainly how to utilize this oxidative cyclization process for really important organic transformation. We can discuss in the next class, and we will also see how various natural product or very complicated molecule can be generated by utilizing this technique, can be of very useful scientific method, right. We will discuss that in the next class. Till then, you please keep studying these oxidative cyclization processes. Bye bye.